Today we'll be talking about calibration methods for small particles. So to set the scene, small particle detection is a growing area of interest, and over time we have seen that the concentration of EVs has continued to increase in the published literature. This is likely due to increases in sensitivity as well as optimization of assays. The real problem though is that no flow cytometer is capable of detecting the full range of EVs. This means that the reported concentration in the literature is not reliable, and it's hard to validate without knowing the limits of detection for these studies. So earlier this year, a position paper was published in the Journal of Extracellular Vesicles. This is a reporting framework that was developed by researchers from around the world representing the ISEV-ISAC-ISTH societies. While the main focus of this work was to provide a standard framework for reporting single EV flow cytometry experiments, a set of minimal reporting requirements was also included. So just to give a quick breakdown of this framework, the first two components are designed to report the assay metadata and include the existing MISEV and MIFlowCyt standards. This also includes some sample preparation steps. The third component focuses on reporting and demonstrating assay controls. So up until this point, if you've completed all of these three components perfectly, you'll have demonstrated that you're able to detect single EVs and you'll have provided enough detail for others to reproduce your assay. You won't, however, have provided enough detail for others to validate your assay. So components 4 and 5 are focused on reporting instrument acquisition and information on calibration and methods for EV characterization. It's these steps that will enable you to derive your limit of detection and report your data in standard units. And this will allow others to validate your assay on instruments that don't have comparative sensitivity. So the final two components, 6 and 7, are mainly focused on data quality control. These include how you decided to gate your data and report statistics, as well as providing your flow cytometry files for others to inspect. So what is calibration? Calibration is the conversion of arbitrary units to standard units. In the top right plot, you can see that if we acquire the same population at 3 acquisition settings on 2 different instruments, we're unable to overlay that population on the arbitrary unit scale. This is where the problem lies when we report EVs that we cannot fully detect and where we have no idea what proportion of the EV population we might be detecting. You can see once we calibrate this fluorescence scale from the arbitrary units to an equivalent soluble fluorophore scale, in this case PE, that regardless of the instrument platform, the optical configuration or the detector settings, we're able to overlay this same population of data and we're able to make fair comparisons. For the majority of flow cytometers, we're only quantifying 2 different signals, the fluorescence signal and the light scatter signal. For fluorescence calibration, we tend to use reference materials that have known quantities of fluorophore on their surface or known antibody binding capacity. This relationship between the number of fluorophores and the intensity in the majority of cases should be linear. In the case of light scatter calibration, the relationship for calibration of diameter to signal intensity is nonlinear. To calibrate this scale, we need reference materials of known size and refractive index. Not only is the relationship between the particles and their light scatter intensity dependent upon the diameter and the refractive index, but it's also dependent upon the optical geometry and collection angle of the system. So this is a more complicated parameter to calibrate when compared to fluorescence calibration, but today we'll demonstrate 2 dedicated software packages that will perform small particle light scatter calibration without needing to know the complex physics required to achieve it. So there are many reasons for why you'd want to perform calibration on a flow cytometer. It will allow you to decide which instrument has the highest sensitivity and resolution, quantify which settings are best for any particular instrument. It'll also allow you to define the limit of sensitivity for your assay and normalize for day-to-day variation. Importantly, it will allow others to validate your assay and lay the groundwork for standardized multi-center studies to become a reality. For the sake of completeness when talking about reference materials and calibration, I wanted to quickly mention validation and quality control reference materials. In the EV field, there is a growing body of literature talking about the need for biological reference materials. While these are going to be useful for developing assays and validating if assays work as positive and negative controls, they're unlikely to be useful as calibrators. Furthermore, the use of beads without quantified units are useful for tracking instrument and assay performance over time as quality control, but are distinctly different from calibration reference materials. Before we go on to demonstrate the calibration tools available, I also wanted to cover concentration as a metric for quantifying EVs. Concentration is a metric that is regularly used in the EV literature and in the vast majority of cases is reported as absolute concentration. We already know, however, that our instruments are not capable of detecting all of our EVs, so this method of reporting doesn't allow us to validate others' findings. For the field to become truly standardized, we need to report the detected number of EVs above a limit of detection, and the way to calculate this limit of detection is going to be by using calibration of whichever parameter the EVs are being enumerated on. Finally, I wanted to demonstrate the utility of calibrating the parameters being used to enumerate small particles. This work was recently published with Vera Tang at the University of Ottawa and was based on a tutorial we gave this time last year at CYTO. The top plots show the detection of GFP-expressing murine leukemia virus, which is approximately 124 nanometers. This was detected at 3 different settings across an LSR-Fortessa and CytoFlex-S. You can see that if I draw a representative gate around the murine leukemia virus on the CytoFlex's plot, none of the virus appears in that same gate on the LSR-Fortessa. This demonstrates the problem of comparing data using arbitrary units. If, however, we calibrate the fluorescence parameter to molecules of equivalent soluble fluorophore and the light scatter parameter to diameter, you can see that the same gate drawn across both flow cytometers is effective. So now with our calibrated units, when we want to report concentration, we can see that the LSR-Fortessa actually wasn't able to detect all of the virus. We were clipping some of the virus due to the side scatter threshold. In this example, the total detected virus at each settings is identified by the black gate, while the red gate takes into account the detectable virus accounting for the limits of detection across the instrument platforms and detector settings. If we look at the detected concentration of virus across the instruments and settings using the black gate, we can see the concentration is higher on the CytoFlex-S, which is expected. If, however, we look at the concentration of detected virus when constraining the gate to the limits of detection across both platforms and settings, which is the red gate, we obtain comparable data. So this is a great demonstration of why reporting concentration above a set limit of detection is going to help standardize our field. It allows others to validate our work even if their instrument differs in sensitivity.